Well, well, well. Look what we hear. An old friend coming back from chapter 11. Our statement today reads, consider a particle in hyperbolic motion. X of t is equal to the square root of b squared plus ct squared, where y and z are 0. A. Find the proper time tau as a function of t, assuming the clocks are set so that tau equals 0 when t equals 0. B. Find x and v, the ordinary velocity, as a function of tau. And then C. Find eta mu, the proper velocity, as a function of tau. What we need to know, of course, is what proper time means and what is proper velocity. Okay? Again, proper here means that this is the time on the moving body. So let's be aware of that. D tau, we saw earlier, was equal to the square root of 1 minus u squared over c squared dt. And then eta, as a 4 vector, the spatial part was equal to 1 over square root of 1 minus u squared over c squared. This resembles the gamma. And then we have times u, the ordinary velocity. All right, moving on then. For our solution, we got to backtrack to chapter 11. And we studied this motion and we found something very particular. We found that the velocity v was equal to c squared t over the square root of b squared plus ct squared. And thus gamma was equal to b squared plus c, and thus gamma was equal to square root of b squared plus c squared t squared over b. Again, we found both of these back in chapter 11, so let's use them. So with this, we use it to find a proper time as a function of t. We have this delta tau rather, is equal to 1 minus u squared over c squared dt. And then what we see is that that's equal to dt over gamma. So let's go ahead and integrate to get the tau off of that dt, or rather the d tau into a tau. So we see here that we have dt over gamma, plug everything in that we found from the gamma. So again, fraction in the denominator, multiplied by the reciprocal. Hence we have b over square root of b squared plus ct squared dt. Again, you can let a calculator run through it. It's pretty simple though, it's just a natural log. Then we have ct plus square root of b squared plus c squared t squared, and then some constant that we have to solve. Remember that at the point where tau equals 0, so does t. We set our clocks that way so we can quickly solve for the constant by setting both t and tau equal to 0. Wonderful. We see that we get some nice cancellations, and we see that k is equal to negative b over c ln of b. What this tells us is that we could factor out a bc from both of these terms, which is what we have here. And because we can use the rule of logs, if there's a minus sign, it's the same as dividing. So we put it all into one proper logarithm. So we see that the proper time tau is equal to b over c ln of ct plus the square root over b. Pretty cool. Now, moving on, we were asked about the position and the velocity and all that other stuff too. But if we know that the proper time tau is equal to this, we can go ahead and solve this for t, and that's going to take a little work, so we got to be careful. So with that, let's multiply over by cb and take the exponential of both sides. So that's how we get, and then multiply by b. So all this is just algebra. C over b over e. So we see how we have c over b tau. That's from moving this bc over. The e comes from undoing the natural log. And then this b gets pushed over, and that's the b we see there. So what we see on the inside now is that we have b e to the c over b tau is equal to ct plus the square root of b squared plus c squared t squared. Why does this matter? Well, we saw that the hyperbolic motion moves in this square root fashion, hence the color coordination. So with this, we just try to solve everything by squaring it and then isolating the ct. So we see that ct is equal to the square root of x squared minus b squared. Again, color coordinating it for a reason. That being said, we could solve everything here. B e to the c over b tau is equal to everything now in terms of x. Wonderful. Why? Well, of course, we're trying to find the velocity, so we have to use everything in order to get rid of things for the position, or excuse me, the position function. That being said, we're going to have to do a little more algebra work. Clearly, to get rid of the square root, we have to minus the x over and square both sides, which is what we do in this step. Be careful when you're distributing. The FOILing can get messy quickly. You see that we have an x squared on both sides of the equation. So we're going to have to cancel both of them. And that's what we see here. Nice cancellation. We also see we have a b squared, so we can factor that out. Yeah, just again, be utterly careful with how we simplify everything. What we're really trying to do is get this thing by itself so we can isolate x after the cancellations. So with that, we isolate x, divide over by everything that's on it. So we see we get a factor of b that cancels. The one b that does survive, we'll just bring it outside the parentheses. And so in the numerator, we still have 1 plus the exponential term after it's been squared, divided by an exponential term. So if we factor out the exponential terms in the numerator, or rather, excuse me, what we're going to do is multiply the numerator by the exponential term in the denominator, because we know that that is the same as writing it to a negative power. Easy peasy. What this allows us to do is distribute into here. And now we see that we take the form of a hyperbolic trig function with an e minus and an e plus over 2. And that just so happens to be b cosine or b cosh c over b tau. Holy moly, that's a lot of work. But we knew this was going to happen because this was hyperbolic motion. So a hyperbolic trig function makes sense. All right, so now that we have the position, let's find the velocity. Again, this is ordinary velocity v, so we got to be careful. So v, we found from chapter 11 was c times ct over the square root of b squared plus c squared t squared. Again, color-coded because we knew what ct squared was in terms of x, and we know that this is x in the denominator. And we have x's to use, so let's plug them in. We found a position here, so we just plugged it into the denominator. Here we have a b squared. The x squared here leads to a b squared cosh squared, so we just factor b out and then push it outside of the radical, which we do here. And as you see, they cancel together. We like that. What's wonderful here is that we can still use Pythagorean identity with cosh squared minus 1 gives us a sinh squared. And the square root and the sinh cancel, and the square on the sinh cancel. So we're left with sinh over cosh, which is equal to the hyperbolic tangent. How cool is that? That being said, we know what the speed is, the ordinary velocity, the ordinary position. Now we have to find the proper velocity for vector for the context. So eta mu is equal to gamma CV00, where gamma is equal to what we found earlier in the context of chapter 11. So again, since we have the square root of b squared plus ct squared, we just put that in as x. So gamma is actually equal to x over b. Easy enough. So if that's the case, we plug in the definition for x via the part b that we found on the last slide, which is the hyperbolic cosine, and we see that the b's cancel. Wonderful. We also just found that the v here was equal to tangent, so we plugged it in. Now we see that we're left with a c on both of these terms, so we could factor that out. So now the proper velocity for vector reads c times cosh, and then we see that the cosh and the cosh here cancel in the tangent definition. So we're left with a cosh and a sinh, and then of course y and z are 0. How cool is that? Hyperbolic motion, hyperbolic trig functions, we're ready, and this all makes sense. Of course, after the fact, a little hindsight helps, but hyperbolics working together, that's freaking cool.